Okay, so hope you had a good lunchtime. So this is the last of our lectures, which I think you'll probably be pleased to hear, because I think having 2 hours in the morning and then 2 hours in the afternoon is a bit heavy. So from now on, all of the finite element will be at 2 o'clock in 138. So don't come here again next week. We're going to be in the computer room. So the plan for today really is just to give you a recap of the two-dimensional derivation, which we looked at last week. I'll then bring in the last two terms, so that's the Helmholtz term and the forcing term. Talk a little bit about surface fluxes. As I mentioned this morning in the exercise, you will set these to 0, but just for completeness, I want to actually cover the process of using these. They actually cancel internally, and at the boundary they give an extra term, but just so you've actually got those full set of notes. And then I'll talk a little bit about boundary conditions. What you will find is boundary conditions end up being quite a large part of your code, just because you have to take into account all of the different sides. So you have a lot of if statements. So I'll try to cover those so you at least know how to implement. And then just the last part of today will be a discussion of best practice in FEA. So if you remember in the assessed exercise, the last two parts, essentially we have a part on we have a part on best practice and just how you use the software. So the idea of this really is for you to get an idea of essentially making sure the code is correct, showing it's validated and verified, and then also talk to the person using your code about how that should be applied. And then the plan really is just to talk a little bit about sort of higher order elements, other boundary conditions, and kind of the wider area. Okay, so we're here week 7, and then we've got now 4 more weeks, and then the assessment deadline 6th of December, that's a Friday, at 4 p.m. So please make sure you're working towards that. I got a question earlier on today about whether or not, when people should start working on this assessment exercise. So my advice is to start now. Even if you're doing just bits and pieces each week, the idea should be you come to these 2 o'clock lab sessions with more work done, so I can help you out. So you come with questions, you've done a bit of work in between, and you've actually then got something you can talk about. If you come here and just expect to do all of the work in those sessions, you're going to get to week 11 and basically not have enough time to finish it, and then you're going to be looking for me, and I potentially won't be able to help you out in that last few days. So please make sure you pace yourself and sort of work towards that deadline. As always, we have the QR code in the corner. So last time we'll do this, and it's basically just please register once a lecture, just to let me know you're here. And then again, as always, you can ask any questions. Now, the purpose of this here, and really this will be the last lecture, but we do have at least a lecture, a PowerPoint screen in the lab room, so I can do at least some of the material. So if there's something you'd like me to cover, something that hasn't been covered clearly enough, please stick it on there, and I can make sure I cover that in the lab sessions over the next few weeks. Okay, so the general case for the assessment question, and then a link to industrial applications and practical tips. Okay, so you've all had time to look at the assessment exercise. This is the form of the equation that you're going to be solving. So it's a two-dimensional partial differential equation. And all of the different bits of this we've looked at various points, the forcing term, the Helmholtz style term. There is this kind of difference here with the diffusion, which I'll explain in a second, but generally speaking, hopefully this isn't completely alien to you. You've at least seen the purpose of most of these terms. Okay, so my advice to you for the assessment, I would start with the understanding of the one-dimensional process. So I spent 3 lectures on one-dimensional case, including the Helmholtz term, the forcing term, understanding physically the form of the equations you should get. So please take the time to go back and really understand that. Work through the exercise we had from last week and actually understand the kind of results you've got. And people have been doing that, and that will be really instructive to you when you go to 2 dimensions. Essentially the process is the same, it's just more mathematics. So if you understand the one-dimensional case, hopefully that will help you when you come to the 2 dimensions. The next point is each term you discretize independently. So the idea here is that actually the process of discretization, using the finite element method, you actually just treat each term individually. So at various points we've looked at various terms, and the understanding of that can be applied term by term if you like. So there's no kind of overall difference here. You can actually treat each term individually. So go through term by term and understand the discretization of those. Do the derivation first before even touching Matlab. Make sure you understand mathematically how the process works, and that will actually give you matrices that should be usable directly in the form in Matlab. If you're weak with Matlab and you haven't done too much, hopefully the forms you get will actually be kind of clear how you use that in Matlab, but I can certainly help you out in the tutorials with the kind of the computing side of it, provided you've done the kind of derivation before. I would say break the problem up, start simple, start with just the diffusion terms equal to 0, and then gradually start to add extra terms in. So don't try to go and solve the whole problem in one go, build up in complexity and think how you can test the solutions, how you can test the parts of it, how you can test that the shape functions you define are correct, to make sure you're testing each part of the code. Then when you come to, so this derivation of the equation is for a single element, and then the idea at the end is we assemble them into a global matrix. In order to understand that process in 2 dimensions, I've given you a triangular mesh plotting exercise, which I think was part 4 of last week's exercise. So use that to understand and use that in your code in order to actually do the kind of assembling of the global matrix. And then the boundary conditions will be really what kind of give you lots of different conditions. So for the group assignments, some of you have said they haven't actually been able to contact the other members of the group. In principle, they should all be members of this course. So please email them this week and let them know that you're ready to work with them and establish a plan of work. If you don't hear back from them by next week and they just don't reply to your email, let me know and I will send them an email and chase them up. So you hand in a single report with your Matlab code, but obviously the assessment is individually weighted. And that's done by both an oral viva that determines who knows what. Ideally, you both know everything and have worked together, but certainly we'll work out if someone has essentially been a passenger. And then you'll say which contribution you made to the project. Okay, right, so just to summary of kind of where we are. So you remember before we solved the kind of one-dimensional solution, which is a linear equation here. Sorry about this. Okay, so over the last few weeks, so the first week we solved just the diffusion equation in 1 dimension. You remember you get a straight line solution, and this was the case, for example, where you've got a gap between 2 moving surfaces, if you like. So the gap between a car and the floor, and you get this kind of linear velocity profile. So we talked about the analytical solution for that, we solved that using finite elements. Week 3, we added the extra forcing term, and that gives you a parabolic profile in 1 dimensions. We then added in this Helmholtz term, and you remember we actually got the sine and cosine terms. Now, thank you for raising this in the assessment exercise, but we're actually missing a square root in this form. So when you go to the general form that includes this lambda term, you need to actually include a square root term. In the analytical solution, the finite element works in exactly the same way. And then last week we considered the FEA solution of the 2-dimensional case. I'm going to review that again today and start to build in a few of the extra terms. Okay, so the one difference that you'll notice with the form of the assessment exercise is we've got this added coefficient in x and y. So just to understand this models difference in different directions. So in the x direction, this coefficient is different than the y coefficient, but also just mathematically in terms of the form you've got here, you can see it's actually inside this derivative. So what I was going to do is I'm actually going to show you the process of how we actually work through and discretize this form using the finite element approach. But mathematically you can kind of think of this modelling kind of fluid flow in, say, a porous media where maybe in one direction it flows more readily than another. So the idea of this coefficient in x, for example, is different from the one in y because it gives different directional flow. Okay, so last week when we talked about the discretization of this, we used integration by parts. What I'm going to show you this week is the same process. Sideways for you? No. Strange. Doesn't seem to recognise which way round it is. The problem is for me it's rotated 90 degrees. Ah, perfect. Okay. Now I can see. Okay, so we're essentially going to look at solving the integral of d by dx kx dt dx. Not too big, no? d omega. So if you remember before, essentially the form we did before was just d2t by dx squared, and we integrated this with some weighting function d omega. So we're going to do exactly the same process here with this kx, which is just the coefficient. Now you've been told that you can assume this is constant inside a finite element. So essentially what we can do here is we recognise that this expression here we can rewrite using chain rule. So if you think about, and this trick is used kind of throughout whenever you come to these problems. It's pretty much the kind of standard trick is basically look at what happens if you integrate by parts, can you rewrite it in another way? So if we re-express it like this, the process of integration by parts gives us d omega dx, kx dt dx, plus integrating the second part gives us omega d by dx, kx dt dx. So essentially, looking at integration by parts of the entire expression, we get this term here, and then this expression which is equivalent to this here. So essentially we rearrange that, and we can show that the expression we have there, we can rewrite as kx dt dx is equal to d by dx kx dt dx minus, let me just put the coefficient there, omega dx dt dx like that. Okay, so it's basically just a process of re-expressing that. So if we substitute this expression here into the original equation, so we have dx d omega, that's equal to the integral of d by dx omega kx dt dx d omega minus the integral of kx d omega dx dt dx d omega, like that. Okay, so all we've done is just rearrange that. Okay, so this term is the usual expression we get when we do this kind of integration by parts, where we've gone from a second derivative down to a product of two first derivatives. And then we have this term here, which we saw before, is essentially a form of surface term. So we repeat this same process with our expression for omega d by dy, ky dt dy, d omega. And we end up with the same expression here for d by dy, wky dt dy, omega minus ky dy dt dy omega. Okay, so this is doing exactly the same thing for the y term. So collecting those two together for the entire expression, we essentially can rewrite this as two terms, and these are the same two terms we've seen before. We have the internal term, which is exactly the same form that we've seen several times before, and this is kx d omega dx dt dx plus ky d omega dy dt dy, and this is what we call the internal term, plus this term, which is d by dx omega kx dt dx plus d by dy omega ky dt dy. Now you may notice this is a slightly different process. I've done a slightly different thing than I did last week. Last week when we had this equation, I did essentially integration by parts. I got the surface term, which are the limits, and then I got this expression for the internal term. And then after doing that, I basically rearranged to give you these expressions. This time what I've done instead is integration basically by parts, sorry, the differentiation here, just using chain rule, substitute that in, and then rearrange the two equations. Just to reassure you, they're both exactly the same process. So essentially it's two ways to get the same thing. The key reason for doing it this way is what you can see first of all is that these coefficients here, kx and ky, are moved outside the derivative. So these are constant, and you're told you can assume they're constant in a given element. So if you imagine a kind of finite element solution made of various different points, you can assume that kx for each element is a constant, which means that essentially these just become constant at the level of the individual elements. which is nice because it means you don't have to do anything else. And then you have this surface term here. Now, this isn't in the form of a surface term. In order to understand why this is a surface term, we have to use the divergence theorem. So this is essentially a statement that the divergence of some quantity, d omega, is equal to the flux of this over the surface. Sorry, let me use the notation. Consistent. A d omega, like this, times the normal vector to the surface. So this divergence theorem is essentially a statement of, when you talk about, sorry, I'm not sure what's wrong with this. When you have a gradient operator inside, that gradient operator essentially shows you the flow in a direction, if you think about it. So this is basically a statement, if you integrate over all of that flow, that will essentially give you the fluxes over the surface of that element there. So this is a statement that the divergence of A integrated over this volume is equal to the fluxes of A dotted with a normal, where this normal is essentially the normal vector in that surface, d gamma. So the reason I've written it in this form is just basically to show you kind of another interpretation of the process. Now, essentially what this means is we can rewrite this surface term here, which we'll call S, and term I. So we can show that the surface term here, we can actually rewrite as the integral over the surface of omega kx dt dx times nx, which is the x component, omega ky dt dy ny d integral. So before, when we did the integration by parts, and I made the kind of argument that the term we had, which you remember before, is essentially the flux at the surface, and I made the argument that that essentially gives you the surface term. This is just a slightly more rigorous way of showing the same thing. Up till here, it's all kind of mathematical steps. So this is just chain rule, rearranging, and then this is just using this vector identity, which you'll find in any textbook on vector calculus. Now, the key reason we've got x and y components is if you think about a triangle. On this surface, this would be the flux dt dx in the nx direction. So we'd only, in this direction, have just the flux over that surface. This is the y surface, so we'd have dt dy ny over that surface there. And over this surface, we'd get a combination of both. So we'd have dt dx nx over 2 plus dt dy ny over 2. So essentially, for a triangle, especially a kind of a right angle triangle, these terms kind of have very clear form. In general, you would always just take the normal vector to that surface at any point. And it's just a physical statement. I mean, if you think of it like a water balloon, for example, the amount of water in that balloon, the change in that would be basically how much flows over the surface. So if you poke a hole in it, the water will flow out of that, and the kind of divergence, the way that water's spreading, is actually defined by how much is flowing over that surface. So it's kind of just a physical statement there. Does that make sense? Any questions on that? So if you compare this with last week I kind of made this kind of hand-wavy argument where I said, if you take integration by parts of d by dx, d2t by dx squared, and you rewrite this, d omega times that, you end up with the surface term, which was just the limits of the integration plus the d omega dx dt dx. So last time I kind of just brushed this around and said there's a surface term that's the surface ones. Like in one dimensions, you get a limit in case. So hopefully that just kind of fills in a few of the bits. And in addition, you've now got how you deal with these extra directional terms. So when you derive this in your coursework, you can see how to get these terms. The form you get should be treatable in exactly the same way. And then you have these coefficients which you can just change per element. Okay, is that okay? Make sense? Perfect. All right, okay, so the next step, if we, just to recap on two-dimensional fields. So when we're talking about the two-dimensional case, the finite element case, we're actually talking in 2 dimensions. Just a reminder that a two-dimensional field is a function of both x and y. So we're now talking about fields that you can visualize like hills, for example, where you can move in either one direction or another direction, and the hill varies in that kind of third direction, if you like. And the colour here just plots that kind of height, that contour. And hopefully you've had a chance to play around with the example in Matlab where you can start to plot these functions. You can also plot it as a surface, so in this case the hill becomes very, very clear. And then just to understand that what these derivatives, these partial derivatives actually mean. They are essentially derivatives of the function in either x or y with the other variable held constant. So you can think of that as basically moving along a line of constant value in say y and taking a slice through, and that will give you essentially the variation in x. So it's exactly the same concept of the gradient that we've talked about in 1 dimensions, just in 2 dimensions. Okay, the one other extra thing I want to talk about is actually these partial derivatives describe fluxes. So, you know, for heat or fluid flow, those fluxes actually describe flows in a direction. So if you have a gradient of dt dx, that's describing the flow of heat in a direction. So typically if you've got an experiment, you'd be controlling, say, the heat flow into that experiment, and that would be essentially controlling the temperature gradient, the flux into that experiment. And even with displacement, so anything in physics where you have a gradient of a quantity, you will see a flow in that direction. So physically you can think of this as things moving down a hill, if you like. So things will move basically to the lowest point if they're moving in x, and then in y they'll move, you know, obviously much faster because there's a bigger gradient. So the 2-dimensional diffusion equation is essentially describing, you know, at the same time movement in those 2 different directions, and those coefficients kx and ky define essentially how much it will flow in a particular direction. So when you come to physically interpret those, if you double one, you'd expect that flow maybe to be less pronounced in a given direction. Okay, so how do we solve this equation? Well, the idea of solving this differential equation is essentially the same as we did in 1 dimension. We write it as in the form au minus f is equal to 0, where a in this case is this operator. So the a operator is basically just everything you do to the dependent variable, in this case t, plus 1. So if we have this as a kind of operator and it acts on t, and that's equal to f. So we can just say everything here is a. Now the reason for writing it in this form is that a will be essentially what you collect together. That's the matrix of all the different coefficients you collect, and that's the k that eventually you end up solving by inverting. So essentially everything in here is the matrix that ends up on the left-hand side of your finite element equations. The right-hand side are the forcing terms. So that's the c term, if you like, in the equations you've got, as well as boundary conditions. Okay, so then we define essentially a series of elements that we're using to approximate our solution. So in 2 dimensions, there are a series of triangles, and we do a least squares fit. So the reason we always have these integrals over, in this case it's an area, but essentially over an arbitrary volume, is what we're doing is we're fitting a series of piecewise functions to the underlying function. So the underlying function is u. Our set of elements are approximating that function by minimizing a weighting function in order to get as close a solution as possible. So the entire finite element process is one of deriving equations that will get a series of linear or triangular approximations to the underlying function, collect them together into a matrix and solve it. So that's the reason for these equations. So we do that for the equation we want to solve here. We essentially multiply each term by omega, and then we integrate over a volume here in order to get the least squares. Now notice, again, each term is independent and separate here. So we have the diffusion term from last week, which is just this one. So we can use exactly the same process we had last week directly. Then all we have to do is just add on extra terms here. So in terms of matrices, you can think of this essentially as just being lots of different matrices we add together at the end. And you'll see when you start working through this, or later in these slides, how that works. Okay, so the steps involved in this, as you've already seen, is essentially we use integration by parts. I've essentially shown you this already here. So again, essentially our process here was one of doing integration by parts. Yeah, I won't bore you again. So that's the process, essentially, to get these 2 expressions, which goes from second derivative to 2 first derivatives, exactly the same process we did in 1 dimensions. And then we have these surface terms here that we've already seen. So just to talk briefly about the surface terms, and again we've seen this, essentially those surface terms you can see are basically a product of the x and y components with the normal vectors x and y. Just for completeness, these normal vectors you can think of as basically being 1, 0, and 0, 1. So they're essentially just saying only take that component in that direction. So, you know, for a perfectly vertical surface, the only flux can be in the x direction. Yes, please.
Sorry, could you wiggle the cable a little bit? The screen's gone yellow.
Oh, wow.
There we go.
Maybe no. Yeah. A nice shade of yellow, right? Okay. Strange. Yes. Okay. So there are flux terms. Okay, so that's that process, and we saw this last week. So essentially, you use integration by parts, you get the terms, you get the surface terms. The next part is to replace those with the triangular approximations. Now, we went through this again over the last 2 weeks. In the same way we did this for a straight line, and you derive an equation for a straight line, what we're doing here is we're using the 3 known values at the corner of the triangle. We're using those to define a function, which is of the form alpha 1 plus alpha 2 times x plus alpha 3 times y. And then we're using the 3 known points we've got to form 3 simultaneous equations. And we're using those 3 simultaneous equations to solve for alpha 1, alpha 2, and alpha 3. This entire process is one of basically just defining a triangle that we know all of the properties of. A triangle is nice because we can solve everything about a triangle. They're well-studied properties since the ancient Greeks. So, you know, using a triangle is very, very nice in terms of we can define exact functions. The process, in order to get the coefficients alpha 1, alpha 2, and alpha 3, is to form the simultaneous equations into a matrix and then get alpha by inverting that array. Please don't get this confused with the overall process of solving the finite element. You could equally, with this particular set of equations, have just solved these directly. All we're doing here is just getting 3 coefficients to define a triangle. There is nothing more to this, it's purely geometry at this point. So we solve in order to get the coefficients for a triangle. Now, I showed you before the kind of starting of how we work through and invert the matrix C. It's a lot of tedious algebra. It's well worth just looking through it, make sure you understand it. It was in the extra notes I gave you, but essentially what you then get is a series of x and y components in terms of the various points, and then what you can do is you can interpret those. So for example, x2 minus x1 is essentially that distance there. So you form a matrix that is of this form, which is, each of these is the kind of contribution to the area for each of the surfaces. And then these are kind of these side lengths of the defining square. And then you remember last week, as part of your exercise, you actually collected those together and got the expressions for n1, n2, and n3. So these were the shape functions. So again, these are the same as the shape functions we've seen in 1 dimensions, but now you can see they're a function of x and y. So, you know, we get this expression for u element, which is a function of n1 times u1, which is at this point n2 times u2, and n3 times u3. So then what's nice, and these are called the constant strain triangles, is the derivatives themselves are constant. So because it's a function just of x and y, the partial derivative in x is just a constant, the partial derivative in y is just a constant. So what we end up with here is an expression for du by dx for the entire element is just being a sum of 3 constants, same for du, dy. Okay, so the next bit is new, and this is essentially how we integrate these expressions. So if you think about what we need to do for the finite element form, I should have included this on this, but we essentially are going to have 2 terms in order to complete the kind of terms we need for the assessment exercise. Omega t, d omega like this, plus omega f, d omega. Now this is just a constant. So essentially what we have here is we're integrating a constant with this omega, and we're going to get an expression for that. And for this, we actually have the product of 2 varying functions, where, you know, this is going to be a function of n1, n2, and n3, and so is this. Now, one of the reasons for using a triangle is actually we have exact forms that give us the expressions for this. And I'll show you this in a sec, but essentially the integral of this would be the integral of this function. If you worked through the mathematics on that, you can actually show you end up just with the integral of the area for this expression. So this integral of just the constant here ends up actually just being basically just an area times f. The integral of the product of 2 shape functions is given by these expressions here. Now for an integral over a surface, it's of this form, and for an integral over a volume, it's of this form. Now bear in mind the A, B, and C are the power coefficients of those matrices. So you can just accept these forms as they are. Now, in general, you would usually just numerically integrate these functions. For more complicated functions, that's the only option, but just here you can just accept these forms because essentially they're just because you've got a nice well-defined triangle, you have a very clear form for that integration. Okay, so let me have a look. Yeah, I was going to show you what I showed you last week. Maybe it's better if I show you briefly just that process. Now let's go through last week. So we'll go through what we saw last week very quickly. Is everyone okay? Do you want a quick break, or this is quite heavy this week because we've got quite a lot to just finish. Are you okay for me to do another 10 minutes and then have a break here? Okay. So this is what we saw last week. The process is basically just taking this product of two derivatives here. We're going to substitute in these constant terms. So the derivative of each of these elements is a constant. So we take basically the two expressions, the omega dx, dt dx are basically just the expressions for each of these times a constant, and you end up with the product of those two expressions. And then what we do is we rewrite them in matrix form. And the reason for doing that is it just makes it easier to process these. So you end up with just basically you can see that we just essentially just collected together the omega coefficients from this into a matrix, and just the b coefficients here into a matrix. So it's exactly the same expression, just rewritten. And then what we can do is we can actually just collect together the b coefficients together in one single matrix. Then we have our weighting functions on the left and just the dependent variables, the things we want to find out on the right here. Just a note on the notation, I've shown this like this, but actually just to be consistent with matrix multiplication, that should actually be transposed. When we come to multiply, I will transpose it, but just be aware of that. Yeah, so okay, so the process really now is just one of integrating, and because this is all constant, it's a constant strain triangle, you essentially can just integrate directly. The integral over a constant is just the area. The integral of a triangle is just the area. So we get the area directly, and we can write that straight in there, and that happens to cancel with the area in the denominator. So the final expression for this term, the omega dx, is a matrix of b coefficients, the omega terms and the t terms. And then for the d omega dy, it's a matrix of a coefficients. Yeah, does that make sense? It's basically just the process of collecting those together. So then the entire expression for the internal term is basically the sum of those two together. So it's the sum of those two matrices, the b matrices and the a matrices. Okay, so the next term to consider is the surface term. Let me just do this quickly. Like I say, this is kind of in addition to what you need to know, because we're going to set the flux as equal to 0, but I wanted to cover this just because in the future, if you have to use this process and you actually want to derive a general solver, it's worth just understanding this. So I'll try to cover it hopefully in a way that makes sense. So essentially what we have is these two expressions, one for the flux in x, one for the flux in y, and then the flux is over the surface here, which is the sum of the x and y components because it's at right angles, at 45 degrees to the two expressions. So essentially what we're going to do is just define those expressions to be b1, b3 and b2. So all we're doing is just redefining them just for conciseness here. What's nice about redefining this is then if this was a more general triangle, then this would be valid for that. So this is kind of more general expressions. And so these are just expressions for the flux. So we need to basically integrate over each of the surfaces for omega, a shape function, times this flux. Now the flux is a constant. Because it's a constant strain triangle, and we're just going to specify them on the surface. So our expression for the surface is basically just the sum of each of the three surfaces we have here. So then the process is just substituting in the weighting function into each of these expressions, and we're just going to do that in vector form, again because it just makes the mathematics slightly simpler. So we're just substituting in for w in this case. Okay, so then we have an expression where we have basically just have to take the integral of these shape functions. Now, to understand how this works, this is a plot of the n1 shape function. So you can see this n1 shape function is 1 at the point n1 in the bottom left-hand corner, and it moves over and it becomes 0 at the other end, essentially. So what you can see is the integral over L13 and L12 are going to basically be non-zero, but the integral over L23 will be 0, because you're essentially integrating over this surface where the shape functions become 0. The n1 function will be different again, and the n2 function. So these are essentially what you can see then is basically we have the integral of this expression, and the n1 term will be 0 for the 2,3 integral. So this surface, the n1 term 0. For the 1,3 surface, the n2 term is 0. And for the 1,2 term, the n3 is 0. So it's just a statement about these shape functions that are by definition only 1 at the nodes and then 0 as you move away from them, becoming 0 at the opposite side. So essentially this process of collecting together the surface terms, you just get a matrix that is L13 times B2 plus L12 times B3. Now, intuitively this makes sense. Basically what you're saying is that the force due to surface terms on node 1 is due to the integral on face 1,3 plus the integral on face 1,2. So, hopefully that makes sense. The whole process of this finite element method is taking the integrals over areas or integrals over surfaces and applying it at nodes. So this is basically the end process of your surface term. Okay, so let me just show you one last thing and then we'll take a break. So I want to just show you mathematically how we derive those two terms. So we've gone through and covered this first term in detail, and essentially that we get the internal term, we get the surface terms, and we know how to treat both of those now. The next process is basically just to look at the integral of these two terms. So this first term is actually trivial. You can see essentially we rewrite it in this form, but what we essentially have is the integral of a shape function. Each of these shape functions essentially gives you a third of the area by construction. So the integral of each of these shape functions essentially just gives you the constant f times area over 3 times this matrix, which is 1, 1, 1. So this integral actually ends up being trivial for a triangle. Now if you remember before with a straight line when we did this integral, it essentially gave you kind of trapezium rule underneath the area, and then what we ended up with was essentially a form that was the length of the line. So it's entirely consistent, it's the same process. We essentially end up with just the force times the area, and you expect it to be this form. If you think about what you're actually talking about, if you have a force acting on an element, and it's acting everywhere on that element, it's a body force, it's a constant force over the whole domain, you would expect it to basically apply a third here, a third here, and a third here, and you'd expect it to be weighted by the area. So the bigger the triangle, the more force you're applying. Bigger triangle experiences more of this force, and the wider the area. So that kind of makes sense, and that's the form you get. Now let me just show you the next expression. Okay, so if you consider the integral now of omega t d omega, and this is over a surface, essentially what we're going to do is we're going to rewrite this as the integral of w1, w2, w3 times n1, n2, n3 times t1, t2, t3 times n1, n2, n3. Does this make sense? So these are basically just w element and t element d omega. So all we've done is essentially just rewrite it in matrix form, and then we do exactly the same trick we did before. Maybe it's because I've got the mouse plugged in. Yeah, okay. So we essentially collect together n1, 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 n2, n1, n3, n2, n1, n2, 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 n3, n3, n1, n3, n2, n3, n3. Okay, and then this is times t1, t2, t3, d omega. So these two expressions are constant here and here, so the process essentially becomes one of integrating just this here, d omega. Okay, so we just basically want to integrate this expression of the product of these shape functions. So this is where that identity I mentioned before, where essentially for a shape function, let's just completeness equal 3, where a, b, and c are powers, d omega, you essentially have this, let me just remind myself of the form. So you essentially have this form where you essentially take the integral over those, and it has a clear expression as the factorial of a, b, and c divided by a plus b plus c plus 2, all factorial. So as an exercise on Poll Everywhere, basically I've left it for you to actually go through and use this for each of those expressions. So to give you an idea how this works, say for n1, n1, this would be basically n1 to a, where a is equal to 2. So it's n1 squared, if you like. So this n2 is equal to 0, n3 is equal to 0. And the idea is you're basically working through and substituting a, b, and c. So if you work through and actually then get the matrix here of expressions. And obviously, if anyone wants to try and integrate those directly, feel free. But I think they're probably, it would be just a lot of tedious mathematics. And like I say, the advantage of using triangles is you don't actually have to, because they're well defined. Okay, so it's the same link as before. I think it's Edward Smith 152. Here we go. So really the process is just, and what you'll find is that there's actually a lot of repetition. So you really actually have to do it for a couple of the different terms. And then what you should get is just an expression for this that is essentially the integral of the product of two triangular shaped functions. So yeah, if you just work through that, and then once you've decided which one is the correct answer. Does that make sense? Anyone completely confused? I don't know. If I give you, I feel bad saying this is a break as well. Maybe we should do this for like 10 minutes and then have a break, an actual break, because otherwise you'll sit on that one. Yeah, maybe take 10 minutes and I'll tell you what the answer is and then take a break. So the process essentially is just one of, let's say, taking those two terms, leave what I put before, and term by term you essentially go through and you just substitute in. So for example, for these terms it's n1, n2, just to the power 1. You stick in 1 for A, 1 for B, and then you stick in 1 into here, and these are just factorial. So this would be 4 factorial, which is 12. So it's 4 times 3 times 2 times 1. And on the top it's just 1 factorial is 1, 0 factorial is 1, so you just end up with basically 2a divided by, so that's 24 underneath. That's 4 factorial is 4 times 3 times 2, so it's 24, sorry. So we have 1 times 2a divided by 24, which just gives you a over 12. If you repeat the same process for n1, n1, you end up with basically twice that expression. So what you end up with is a matrix that's a over 12, with 2's on the diagonal and then 1 on the off-diagonal terms. So, two things to take away from this. The first is that this is just an expression that makes the process of integration easier. I'll talk towards the end of this lecture about how we do it more generally with integration. For the purpose of this assessment exercise, you're just going to use triangles, so you can just use this expression. But essentially what we have done here is integrate the shape functions, or the product of two shape functions. So this expression here, which is the product of these two triangularly varying terms, the product of those two essentially give you a constant matrix that's multiplied by that. So this is the matrix that you will actually add as an extra term in order to include the Helmholtz style term. So just to kind of put the whole expression to kind of give you the picture. So this internal term is what we saw last week. So this is basically, the color coding shows you where they came from. So you remember we split the red expression here into an internal part and a surface part. The internal part, because it's a constant strain triangle, are two matrices of constants. We integrated those directly and just got an area, which cancelled with the area squared underneath. So this gives us essentially the terms internally. The surface terms, as we've already seen, are obtained basically from the integral over the surfaces. So the surface terms on each of the nodes is basically the sum of the fluxes over each side. We now have this Helmholtz term here, which is basically the integral we've just seen, that gives you this matrix with 2's on the diagonal. And then the final term here is the forcing term, which is the right-hand side, and that was just the direct integral of that forcing expression. Okay, so if we, so maybe I'll give you a 10-minute break now if you want to get up and walk around, and then we'll finish off this derivation afterwards. Okay, so any questions? I've left that on. Sorry, I realised the yellow is not an ideal colour. It's clearer on my screen. It's kind of golden, but that looks. Okay, this should say FE in this corner here. So this is the forcing term. So anyone got any questions about this? It's all okay. So it's essentially this process of rewriting this differential equation as a series of matrices. Bear in mind this is for a single element, this expression here. So the next step will be to assemble it together for a collection of elements. So what we're going to do is just collect together and just rewrite them in matrix form. So basically the K here is the internal term, P here is the surface term, HE is the Helmholtz term, and FE is the forcing. So again, just to make it clear, all we've done is just rewrite these just more concisely in this notation. Okay, so coming back to our kind of overall process, in order to solve this equation, we use the integration by parts that I showed you at the beginning, and that just re-expresses this term as the surface term and two first-order equations. We then replace T and W by the triangular approximations. So in this expression, it's the derivatives. In this expression here, it's the product of those two terms that we've just used that expression to get the integral of. Here, it's basically just this expression times force that you remember just gives you the area directly. So what we've then got is essentially left-hand side and the right-hand side. And the key point about the left-hand side is they're all multiplied by the T terms, and everything on the right-hand side doesn't. So you can see, you can predict which terms are going to be on the left-hand side by the fact they have a T dependence. So here and here, they're the terms that are going to end up on the left-hand side, and then the forcing terms will be on the right-hand side. And so the next step is then to collect together each of these expressions, which bear in mind are for a single element into simultaneous equations. So just to kind of go back over this process for each of the triangles, if you think each of those triangles, if you put them together in a grid, and we talked about this last week, so this is essentially a case where we have 12 elements, which also has 12 nodes, forming a grid. So what we've just derived essentially is for one element, and the first thing to do is to actually write a table of elements and the individual nodes. So for element 1, you can see it has node 1, 2 and 6. For element 2, that's 6, 5 and 1. And you'll do this in Matlab. In the actual Matlab code that I gave you, and this is question 4, you can see we actually define this connectivity in an array trie directly. So the first thing to do is to set up the domain size, set up the number of points. So these are the number of nodes, if you like, and the nodes just form a grid. And then what we do is we loop through both x and y, and essentially we form a grid of all of the different points, and we store them as an array x and y. And then what we're doing is we're defining this connectivity matrix. So you can see this is essentially defined by hand for a very, very small system, and that's fine. You can do that easily enough for a small, simple system. On the right-hand side is how we plot that. So I encourage you, if you haven't, to go through and just plot this yourself. Convince yourself this is essentially giving you the same form as we're solving here. And someone was asking about working things out by hand. I mean, it's always a good idea just to kind of go through by hand initially to understand, especially if you're not good with Matlab. Try it by hand, just understand the process, and then it will make it much easier when you come to do it in Matlab to essentially write code that just does what you've done by hand again and again and again as a loop. So this process of defining a matrix of a table of different values, we've just written them as a matrix here. Now, in order to do this more generally, there's essentially a function that allows you to do that, and that defines this trie matrix. Now, one thing you'll notice between here and here, well, firstly, I've increased the number of elements just to show you a kind of more general case, but the other thing to notice is actually the way the elements are defined has changed. So we've actually got triangles the other way around. Now, what you'll find is that actually gives you a different local matrix and a different, potentially different global matrix. But the key point is actually this doesn't matter. As long as you're consistent with the convention you use, then it will not matter and you should get the same solution. So more generally, I encourage you to use this function here. And again, that's in the exercise in order to set up your grid of triangles. Okay, so just to understand how this works in terms of assembling the global grid, for a given triangle, B1, XY, so with 1, 2, 6, for example, this element 1 in the bottom left-hand corner, just for the kind of derivative term here, which is looking at those terms, you remember last week we looked and showed that you can actually just sum up the different coefficients. So this is now in terms of B1 and B6 for element 1, which has 1, 2 and 6. Now, if you remember, we worked through and we used the case where this is actually of size 1 in both directions. So because it's a right angle triangle, it makes it much simpler. Lots of terms become 0. And you worked through this yourself last week. We saw that we had a K matrix that essentially just is of this particular form. So this process is one of just going through and substituting in the numbers. In Matlab, you'll do this automatically, but we did this by hand last week, and you saw hopefully that it gives you this form. Now, if we look at the second matrix, second element, number 2, which is 1, 5 and 6, the matrix is now in terms of B1, B5 and B6, and you can see then that the actual two, if you look, the two matrices are actually different. Now, instead of this one is in the top left-hand corner, the bottom right, you can see essentially these two are flipped over. But the overall matrix you get for this is exactly the same. So the key point here is that for a right-angle triangle, the element is identical. So that's the first thing. When you write your code, you should start with this simple case, and you should check that this is true and it's fine for every element. The code you write in terms of A and B is general, can be used for any triangles. But essentially what's nice about using these very, very simple triangles is you can do checks against what you expect by hand, and then you can go to the kind of more complicated cases. Okay, so coming back to our expression here for the entire system that includes the surface terms, Helmholtz terms and the forcing terms. The surface terms, if you remember, were basically a generalization of the 2D case. And essentially what we have, and you remember we saw this in one dimensions, is on the nodes we have two fluxes, one from each element, and they cancel out with each other. We can see exactly the same thing here. So all internal fluxes cancel. And this is nice. It basically means all of the fluxes over these diagonal elements are cancelled. So the only fluxes you would have to worry about are the ones at the boundary. Now, physically, this makes a lot of sense. Intuitively, with a problem you're solving, you essentially, if you've got a plate that's, say, vibrating or you're heating, it's entirely defined by the values at the boundary. You're essentially solving a series of equations that describe the physics inside, and it's the boundary conditions that entirely define the problem, the values at the edge. Mathematically, again, when you solve differential equations, and we've done this a few times integrating them, you get two unknown coefficients. Those two unknown coefficients in one dimension are essentially the boundary conditions. Here, if you could integrate these exactly, you would have essentially the number of boundary conditions as the edges of the elements, if you like. Now, in your exercise, you're required to do a zero flux condition and a specified value of t. So the zero flux condition, essentially, you'd just be setting all of those b terms equal to 0 at the edge. And for the specified value of t, I'll show you how to apply that in a sec. The first thing I want to show you is just how we simplify these equations. So the first thing is we now know that these surface terms are always equal to 0, partly because we essentially cancel internally, partly because for this exercise we're setting those always equal to 0. Now for the last part there was an optional extension, and if you want to try to look at maybe non-zero fluxes, that's one possibility if you're interested in applying those boundary conditions. You at least have the mathematical framework to be able to do that. That's of interest. Okay, so the next step is we're going to cancel these weighting expressions. Now remember the argument last week about the scaffolding. Essentially now we no longer need those. We essentially have these three weighting functions which we've chosen deliberately never to be 0, and essentially what we can do now is just throw them away. They're on both sides of the equation, so we can get rid of those, and the equation we have left now stands by itself and essentially is an equation that is the minimized solution to a series of triangular elements describing the differential equation we want to solve, which is this one here. Okay, so then essentially what we have, if we substitute in the expressions for the right angled triangle, which has an area of a half, and as we said before, A2 and A3 values of 1. The A1 value is 0 because it's right-angled triangle. If you remember looking at it before, essentially these expressions disappeared. If we substitute in the numbers into the internal term and the Helmholtz term, you can see we essentially just have a matrix of just numbers. So in the specific case, and again this was a question we had, in the specific case, it's worth doing this, just trying it with some numbers, making sure the form you get makes sense, but make sure the derivation you do is general, and then you define this in terms of variables, and in Matlab you then solve, and you can change those values later on. And on the right hand side we have f over 6 term. So what we're going to do now is we'll basically assemble and add those two together, so this is just the sum of those two together, which is just essentially just adding some numbers together and collecting together a common factor of 24. And this is multiplied by t. So this is our matrix K, this is t, the values we want to work out, and the forces on the right hand side. So the next step is to assemble the global system. So this is the equation for one single triangle. What we're now going to do is substitute those values into the global matrix. So for element 1, which is in terms of 1, 2 and 6, we basically go through and put these values into the corresponding points for T1, T2, so I did this before, but T1 for example would have this value, and this value here, as well as this value and this value here. So you can see it's just these expressions essentially here, here and here. And similarly for T2 and T6. So it's just a process of going through and putting them into the global matrix. You do the same thing for element 2. Notice also on the right hand side we're also adding the forcing terms. So these forcing terms are being added for each of the elements based on T1. So you see because T6 has occurred twice, we get twice the force on that. And again this makes sense because when nodes meet you'd essentially expect twice the force due to the surrounding elements. And so eventually once we go through this process and put it all together into a single matrix, you can see we have this overall matrix of all of the different coefficients. On the right hand side we have all of the forcing coefficients. And essentially that's our global solution. So that's the process. Does that make sense? Any questions on that? So you're going to do this in code, do this within Matlab code, but the process really, get the local elements and then just put them together in this global using a loop. You might find that being one of the tricky steps, actually working out exactly how you loop through and collect the global ones in the correct way, but essentially it's a problem of indexing. Bear in mind in Matlab you can kind of do the same indexing you'd normally do. So you can take elements I and j, for example, of the K matrix, and you can put them into the global matrix. So I personally would do something like K global, and then you're getting the values of, say, this would be I global, for example, and J global, and these are going to come from that tri matrix, which was essentially the one for the global selection of values. Now, I'm not expecting you to understand this straight away. This is something that you have to kind of first of all get your head around how we actually express the triangles. Once you understand that, it's purely just understanding how to put things into a matrix. So this is really just the kind of computing bit. Everything up to now has been kind of mathematics. But once you've done that, you can assemble all these kind of global matrices together. And then the last thing to do is to apply boundary conditions. So as we said before, the Neumann conditions, which are just the zero flux boundary conditions, we can specify directly. And that's essentially just setting, you know, the flux is equal to 0. For the fixed boundary conditions, it's slightly more tricky, but it's exactly the same concept as we used in 1 dimensions. That is, we essentially take, for example, T4, which we know is going to be fixed to t equals 0 here. We take that particular column, T4, so everything that's multiplying T4 in this matrix, which will be this row here, we basically cancel out and set to 0. We also then get rid of the fourth row. Similarly for T8, T9, T10, T11, T12, we basically cancel all of the rows and columns that correspond to that. So that's 8, 9, 10, 11, 12, these values here. So in doing that, we essentially then reduce our matrix to a kind of simpler form. Now, if you remember before, I just basically wrote a kind of shrunk matrix. In Matlab, what we do instead is we actually set those elements equal to 0. So everything is set to 0 in a row which is fixed, apart from the diagonal, which is set to 1. Now bear in mind we've got a 1 over 24 outside, so in this case it's 24, but essentially what we're doing is we're setting that row to 24 here, just to understand this here. So this value of this here was basically just an equation where it multiplies T4 here and T4. So as we had before, this is just a statement that T4 is equal to T4. So we've essentially reduced that to a trivial equation. That's the definition that the boundary condition has to be enforced. So again, you'll do this in code. You have to use if statements, you'll have to loop through, find the boundary conditions you want to set to 0, and then you actually apply this particular condition. Does that make sense? Okay. Next one I want to cover is just a non-zero boundary condition. So this is the case where we're going to set the bottom one as equal to t equal 100. So essentially the process here again is we cancel the rows and columns. Again, we've got 9, 10, 11, 12. We've set equal to 0 here, so we've just cancelled those. For the bottom ones, we've also cancelled those rows. But what we have to do then is, if you remember, we move the matrix to the right-hand side and multiplying it by the value. So essentially what we're going to do is we're going to take this entire column here, and we're going to move it to the right-hand side and subtract, say, for this one, this is T1, times that matrix. So this would be 92, sorry, I think that's minus 92, 49, 0, 0, 49, 2, and then zeros down to the bottom. For the next, so that's for essentially T1. For T2, we do the same thing. Now, why do we do this? If you remember before when we solved simultaneous equations, when we knew the value of a simultaneous equation, it meant that we could take that value, stick it in the equation, and then move it to the right-hand side. And you're then solving for one fewer set of variables. So it's the same process here. Essentially, we can just move this known variable here, T2, and this is multiplied then by that column there, which is 49, 186, 49, 0, 0, 98, 2, 0, 0, etc. and so on. Now just for this last one, I'm just going to show you in Matlab notation. So essentially what you can do is you can say that this column is essentially K, let me get this right way around, I think it's semicolon, this would be semicolon 3, for example. So essentially we'd use just that column. I think that might be the wrong way around, but essentially then what we'd have here is minus T3 times K semicolon 3 and so on. So in general matrix notation you can actually do that and move that to the right hand side. So that's the process of applying. And bear in mind that, you know, in this case we've set T3 equal to 100, but you could then set that to whatever value you wanted to. Yeah, does that make sense? Okay. The reason I keep asking is because you're going to have to do this. And obviously you can ask questions in the in the Matlab sessions, but what's important I think here is understand the principle. Obviously this is recorded, you can view it back, but over the weeks, if some of these things are not clear and maybe you've forgotten how this works, then please send me an email on Blackboard, and what I can do is I can actually go through it again, maybe on that kind of projector in there, just to kind of remind you, because you'll probably be at least a couple of weeks before you come to the boundary conditions. Yeah, so that's just the same thing written out. Okay, so that's pretty much it for the derivation. That's everything. I just want to talk to you now really just about slightly more general best practice and a few other bits and pieces of finite element analysis. Now these essentially are kind of things that will come into the last two parts of the assessment exercise. As I said, I'd like it if you could actually go away and read some of the literature, look at other best ideas for best practice, try to incorporate a few references. But this really just gives you some kind of ideas about how generally you should be conducting the finite element in the context of what we've done so far. So the first thing to mention is other boundary conditions. So we've talked about direct boundary conditions. These are things like velocity, displacement, temperature, depending on the physical situation you're talking about. The fluxes, would be in this case strain rate, strain, or in this case heat flux, so dt dx. And in terms of interpreting this equation, you should talk in general terms, but probably heat flow is the simplest one for your assessment exercise. Then you have these mixed boundary conditions that can be a combination of, say, the first derivative and the value itself. You also then have symmetry boundary conditions. Now, symmetry boundary conditions are useful if you want to reduce how much of the problem you want to solve. Now, this is an example of the two-dimensional diffusion equation on the case we've just seen, made slightly bigger, just 3 by 3, with an applied force. Now, if you think about what this actually is, this is essentially, if we slice through here, you can think of this being the parabolic profile we've seen before. And you can think of this being like flow in a pipe. If you've got fixed at the walls and you apply a force, you'd imagine you get a kind of parabolic profile. Or if you've got a vibrating, that's probably a worse example, if you've got a heated plate and you've got a fixed temperature at the wall, you get a kind of heat distribution. So what we can do, you notice about this problem is it's actually symmetric. We're actually solving far more of the domain than we need to. If you think about it, we could actually draw a line of symmetry down the middle. We'd actually halve our computational cost. We'd still be able to get the same solution in terms of the parabolic profile. Or you could do it again and actually just solve a quarter of it. Arguably, you could actually go to 1 dimensions and get the same solution. But, so one thing you should be aware of is using boundary conditions to actually make the problem cheaper to solve, such as symmetry boundary conditions. And the idea of this is they essentially allow you to essentially solve a smaller problem. The other type of boundary conditions worth mentioning is periodic boundary conditions. And that is, if something goes out one side, it comes back in the other. If you think of the game Asteroids, where if you fly out one side, it comes back in the other. I don't know if you can see this, but your little ship flies out this side and it comes back in here. And this, physically corresponds to, let's say, we've got a pipe where the walls are fixed, and essentially what you'd have is you'd have a flow in that pipe, and actually the best idea is to keep putting the flow back in again, so you can model a much, much longer pipe computationally much more cheaply by using these periodic boundary conditions. So again, these are other possible boundary conditions. For your problem, you only have to worry about the first two, but just so you're aware of that. So some general modelling guidelines. Keep it simple. So the more complex a model is, the more chance of error you have. And you'll see this with your exercise. The more terms you incorporate, the more chance you'll make a mistake. So you should always stop and think, can you make the problem simpler? Can you model just, say, a small part of the problem? If you want to model an entire car just to find out whether, say, the wheel will fail, can you model just, say, the axle? Or can you model just, say, part of that to actually reduce the problem down? Can you use a 1-dimensional or 2-dimensional solver instead of the full 3D model? And even if you plan to do a full 3D model and stick it in analysis, can you do a really simple case first of all that will show you some insights, to give you some physical intuition before you move to the more complicated case? And it's always worth doing this, because even if the model's too simple, at least you get some physical insight first of all before you move on. This is kind of general advice with FEA in general, but again, for the process of the assessment exercise, you'll kind of really hopefully start to understand this, is do not go straight in and try to do a full complex solution and make sense of it. Try to break it into parts that you can understand individually. So we talked a lot about the physical interpretation of things. Can you apply a case with just a sliding top wall? Do you get a linear solution? Does it make physical sense? Is that what you expect to see? If you do this, you identify not only like errors in your code and bugs, but you also identify maybe points where the model you're using is not correct. So the simpler the problem, the more chance you'll spot errors. Does the solution change when you add more elements? And I'll talk a bit more about this in a sec. Can you match the solution to analytical or other modeling methods? Do you have previous solutions where you knew the code worked correctly to work backwards? And then finally, experimental results. And generally, it's quite difficult to find good experiments that you can match. But really, these kind of analytical cases for the simple ones are worth doing. Other modeling methods. So, for example, with this exercise, use ANSYS. Set up the same case in that, and just check that your solver is doing the same thing. In principle, you should be able to get exactly the same results as ANSYS. If you don't, then why? It's an interesting question. So, when you have an error, in terms of frequency, probably the most common is coding error, and mostly will be you mistype something, forgot to set a variable equal to 0, something very, very minor in your code. Maybe you forgot, you've used A when you should use B, for example. That said, they're very, very common when you write your own code. It's very, very unlikely that you'll find a coding error in a commercial or even open source project. Lots of people use these. So if something goes wrong, don't immediately assume it's going to be a coding error on their part. It's probably your own mistake at some point. But certainly for your own code, be very, very aware that it's so easy to make mistakes. Make sure you check everything work in your pairs and make sure you check each other as you work. The next one is input errors. So these are basically wrong or incompatible boundary conditions. Maybe you've put in the units and they're actually the wrong magnitude. So you've scaled something incorrectly. Very easy to do again in commercial solvers. Maybe you've converted something wrong. Then you've got numerical errors, things like poor mesh resolution, poor mesh shapes, or a badly conditioned stiffness matrix. And I'll talk a bit about that later. And then the last one is, you've got the wrong model of reality. And this is why starting simple is best. Start with a too simple model that gives you something and then build up the complexity. If you make a really complex model, maybe you've included all the physics, but maybe you've got too much. You end up having, effects that aren't really there. Okay, so I talked a bit about this morning about verification and validation. So the distinction between these two. Verification is to test the software is free from basic bugs and errors. Now, from the point of view of your assessment, it's enough for you to say, I stuck a breakpoint in and I stepped through the code and made sure it's correct. It's enough to say, I've made sure that the output of this, plotted against, so the shape function, for example, I've made sure that the sum of the shape function gives 1. I've made sure that the shape function, I plotted it and it's linearly varying. Make sure you check these, because even going through this myself, is only when I came to do that I found there was an error. And what you can find is 2 errors typically cancel each other. You get the right solution overall, but individually the bits don't work. And then you actually find, that will come up later on. So think about how you can test each individual bit and make sure you build up lots of bits that you're sure are correct. And as an engineer, this should make sense to you. Essentially what you're doing is you're making sure, each part of your, whatever you're making, whether that's like a car, for example, you're making sure each part is correct before you put it together. It's kind of common sense with that. So that's how do you show you've written the software correctly. The validation is to test that the physical model works as expected. So that's really saying, is it giving the physically meaningful results and the expected outcomes that you want? So this is where you match to analytical solutions, you match to other FEA solvers, you make sure you're giving the user what they want. Now, in the exercise, you've been told exactly what the equation should be. So you know what form the user expects, but you need to make sure that each of the terms is giving that. So that's showing you've written the correct software for the problem of interest. More generally, this is advice for FEA. So a bit on software best practice. Unit testing is worth mentioning, even if you don't actually employ it. Just look this up. It's an essential technique in software development where you write the software in parts, in functions or in bits and pieces, and you test each bit individually. So this is kind of the idea of quality control in engineering. The reason we have 10-year warranties on cars is because it's made of individual parts bolted together, where each part has been designed to a high standard by an individual company that specializes on that. The same analogy for software. If you think of a function like a contract, so let's say the square function here. The contract is, I give you some value x, you're going to return the square to me from that function. So I know exactly what it should return, and I can test that, and I can make sure that function returns what I expect. If it returns the wrong thing, if I pass in, say, 2 and I get 5 back, I know that's a mistake. So the idea really is to try to think of your software, how you break it into bits, make sure they're all correct, and then put it together. So you're testing it as a series of units. It's not clear how much you can do in this particular exercise, but firstly, it's worth being aware. This is best practice. Any company you work for in software does this as standard. And as engineers, this is really very, very much in line with your training. And also just in terms of actually just testing each part, make sure it works. Think about how you can do that. The other thing is version control. So Git's the most common. It's worth thinking about setting up a GitHub account for your group. So this keeps a record of the changes to the code. And the idea is when you make a mistake, so let's say you worked on it last week. At the end of the exercise, you basically save it on there. It will, when you save it, you commit with a log message. You say, oh, I've been working on the code, I've implemented this bit, stuck in this matrix, put in the boundary conditions, here's the code. And it will tell you basically a log message that tells you why you've made that change, the time, and who did the work. Now, the advantage of that is that when the code stops working, you can go back to the previous version. You can look at what mistakes you've made. It also provides one single source of code that you work on together, and you can also look at the history and see essentially changes from that. So it's a bit like Dropbox, but for code, with a complete history of every step and a log message to tell you why you've done that. So I'd recommend it for group work. I'm not going to insist on it just because it's another thing for you guys to learn. But again, if you go to work for any company that uses software, they will be using version control, most likely Git. Okay, mesh resolution. So we've talked a lot about straight lines. Now resolution as a concept hopefully is very clear from pictures. If you look at the difference between these two pictures, the top one's much worse resolution than the bottom. And that's to do with the fact that pixels individually are essentially larger. So they're a worse representation of the true picture of Neumann here. So essentially, if we use more elements, we get a better approximation. And so one of the exercises we had was to actually, explore that and to look at higher resolutions. For the Helmholtz term in one dimension, if you look at that, if you use fewer elements, you can see there's a big error between the correct solution. The line here is the analytical solution. The points here are the finite element solution. So you can see, essentially we've got some error here, and as we go to higher and higher number of elements, we're getting closer to the true solution. So how do we quantify that? Well, one thing, if you know the analytical solution, you can quantify the error against the analytical solution as a function of the number of elements. So this is a plot here of essentially just increasing number of elements versus the analytical solution. So I just take the sum of the error between the two and plot that as a function of number of elements. So one thing you can see is that gets smaller and smaller. But bear in mind this is a logarithmic graph. So you can see that the rate at which it gets smaller becomes slower. So increasingly it becomes less and less efficient. So essentially you have to get to a point where you say this is accurate enough. And this is one thing about this is it's always an approximation to the true solution. Now obviously you don't normally have the analytical solution, so you can't compare the numerical to the analytical. So the other thing you can do is a mesh resolution study. So in the exercises you're told if you can to compare to analytical solutions, compared to ANSYS or something like that if you can. If not, then you do a mesh resolution study to show that you've converged to the right value. So what I've done here is I've taken that solution here, and I've basically just taken the sum of the area under the graph, for example. It's just some metric for that. And what you want to do is you want to plot that as a function of the number of elements to get to the point where the solution stops changing. When you reach that point, at least you know that by refining the mesh further, you're not getting closer to a solution. You've essentially converged to a solution that hopefully should be closer to the correct solution. So it's worth doing this in your code when you're actually looking at a problem. Make sure you keep increasing the resolution until it stops changing, either at a point or in an integral sense. Okay, so one of the big advantages of finite element method is that we can actually do it for non-uniform meshes. So before I showed you a refinement, with this case actually it's much more efficient to define local smaller elements in a region where it's varying more quickly and bigger elements where it's varying more slowly. And this is one of the nice things about designing something as a series of lines. We can make the lines different lengths. So in one dimensions, H would be different for each element. So the stiffness matrix, the local stiffness matrix would change, but essentially the process will be similar and the code will be similar. So this is one possible extension you could think about, is actually implementing non-uniform elements to get higher resolution where you need them. One thing about numeric, so remember the whole purpose of this process is to form together this big K matrix of coefficients, and then we're going to invert it in order to get a solution for U. Now this can be done, this inversion process can be done in many different ways. I showed you last week the kind of direct inversion. That's where you go through and you get a matrix of cofactors, the determinant, and you work that out. Then there are kind of algorithms for this, LU decomposition, Gaussian elimination. And then if it's a tridiagonal, that is a very very concise matrix, then you can use these kind of very, very efficient solvers. So one thing to bear in mind is the more ordered your mesh, the easier and cheaper it is to solve. So what you see in some commercial software is they actually spend time reordering the numbering on the elements. So I mentioned before how, depending on how you order it, you'll get a different matrix. This is an example of that. So this is a perfectly uniform mesh, and you can see it essentially just gives you a very nice diagonal global matrix. When you start to introduce, say, less and less ordered matrices, you can see you start to get slight spread there. And in the more extreme case, when you've actually got a very, very disordered mesh here, you start to actually see a very, very spread out matrix. And this would be much more expensive to solve numerically. So just to be aware that the kind of the nicer your matrix is, the kind of more ordered your matrix, the easier it is to solve. And again, you know, it's to do with the numbering of the actual elements as well. So ideally, they should be numbered in a way that basically means the connections are form a matrix that is as neat as possible. Doing this by hand is very, very easy to do that, but automatically is quite tricky. And so the other thing is higher order shape functions. So instead of using more elements, instead we can actually use instead of using straight lines as an approximation, we could use, say, a polynomial as an approximation. So exactly the same argument, they meet at a point and they're equal at that point, but instead our line is now a function of x squared plus x, or we can even go to cubic or any arbitrary polynomial. So this would be, remember before we looked at kind of the solution of lots of straight lines for a solution of, say, a second order function. Actually with this you could get an exact solution for that. So sometimes it's better to use higher order polynomials, and then you can use fewer of those polynomials rather than lots of straight lines. So just be aware that this is a possibility, and you can work through the mathematics, and essentially it's exactly the same process of just forming a matrix just with kind of higher order terms. There's a whole range of specialist elements, trusses, beams, thin shells, springs, which in one dimension you can use for particular cases, more for solid mechanics. Same concept in 2 dimensions. We talked about a triangle. We could also go to a triangle that has extra nodes per side, and that's the same concept as a polynomial each side. We could also use what's called a bilinear element, or sorry, this is essentially a square cuboid element, but has a bilinear approximation. So you can see it has 4 points, and essentially the process would be the same as deriving this element. You put in a known values, you solve the matrix, you get an expression for that, and you have higher order versions of that. So this whole process is one of approximating as a series of functions. There are times when squares are better. And then in 3 dimensions, we can go to cubic or brick elements, tetrahedral, brick triangle elements, and we can add extra nodes per side, as well as a whole lot of specialist elements like membrane, plates, shells, etc. So you've probably seen all of these with ANSYS, but just be aware that the theory we've talked about is exactly extensible to this. For example, you could derive these equations in exactly the same way, just more mathematics, more complex. The big problem we talked about when we did the exact solution of the integral of the triangle, one of the nice things about a triangle is we can get an exact integral. More generally, we could either use a mapping function, and that makes some of the mathematics simpler. So often we will use a mapping process that essentially goes from a kind of non-uniform mesh to a uniform mesh. And again, this makes the integral simpler. And there's well-defined processes for doing this. I'm not going to talk too much more about that. The other thing is, because essentially we're evaluating these integrals, we had for the triangle this exact form. More generally, if you want to integrate any particular shape, probably the best thing to do is Gauss quadrature. And essentially that provides a general formula that you can use to integrate any shape function you want. This process, if you wanted to do a finite element solver for more complicated functions, you would essentially just replace this expression here with a Gaussian quadrature of arbitrary order, and that would give you the way of integrating. But otherwise, the process is very, very similar to what you've seen. So, quick mention of mesh quality. So what I've done here is I took the solution of the solution we had earlier on with the forcing term and 0 at the boundaries, and I just basically randomly moved some of the points. And you can see you've got a much more distorted form of the expression there. So just to be aware that you want to be careful about the shape of your elements, and this is to do with mesh quality. Really, you want to take care of your mesh. A bad mesh gives you bad results and a bad impression if you're using this as a kind of consultancy. So modern meshes do lots of things for you, but general kind of advice is finer meshes in regions of rapidly changing gradients. So that makes sense. You're basically putting more resolution at the points where it's changing more rapidly. You saw that with the one-dimensional case, with the straight line, where I put more locally. And then the question is, do you use linear varying or more higher order elements? And again, that's a choice, but be aware that you need to make sure you're not connecting higher order elements to lower order elements, which will cause gaps essentially. So you want to make sure your elements are consistent. You want to avoid sudden changes in element size. So typically you want them to kind of gradually increase in size. Physically this makes sense because if you've got a gradient and a much larger element, you essentially get numerical errors proportional to the size of that element. So you want to make sure that you're kind of gradually increasing that. And then just to be aware that it's fine to mix, like say, triangle and square elements, and essentially you probably want to use a triangular element if it's triangle rather than a really deformed cuboid element. So use the appropriate element for the problem of interest. So this is, say, one example where you'd use a triangle here, you'd link it to a cuboid. The cuboid you'd map to an arbitrary space, and that would allow you to solve, say, this type of shape. So in terms of FEA software, what you're going to do now is write your own, but be aware that the Matlab code or even something like Python code will be too slow to use in general. So if you do want to write your own FEA solver in the future and you actually want to use that, consider using a lower level language, a compiled language like C++ or Fortran, because you'll find Matlab is essentially not usable for big system sizes. The advantage is you understand how it works. You really would be able to kind of really tune everything about it, but you're limited to simple problems. Do not assume you have to use commercial software. There is a whole range of open source software that's worth investigating. I would say if you learn this, it's a useful skill for employers. If you go to an employer and you say, I know how to use open source software, it means they've saved £2,000 or £3,000 a year in license fees if you can use one of these. So just investigate some of the free open source software. Some of them even have graphical user interfaces. Phoenix is kind of like a general framework. FreeFEM++ has a GUI and a long history. I've not used Goma, but generally you want to look for basically how many people are working. If lots of people are working, it's got good support. You can go to the community and you can ask how you do certain things. So it's well worth thinking about this if you're planning to use FEA in the future for whatever application. And then obviously you've got the commercial software. They make it very easy to use, probably too easy, because it's easy then to make mistakes or just create meshes that are really bad. But if you start to use bigger jobs on a supercomputer, you pay per node license. Supercomputers have thousands of cores, so you're talking 1,000 times 3,000, really big amounts of money. So again, the open source software is advantageous, but there's a big list on Wikipedia and other sites, so spend some time researching what's a good option. So that's it, that's everything I wanted to say today. We've got about, pretty much maybe 5 minutes if anyone has any kind of burning questions on how to do things for the assessment exercise or anything else, but otherwise I will see you next week at 2 o'clock in the computer room. This will be open all week, so again feel free to stick suggestions for things you want me to cover again if you are working on this and you want extra things, but yeah, thank you.